Okay, let's begin our today's seminar. We have 3 speakers, and this will be pre-defense of students' course projects, 3 students from Faculty of Computer Science and School of Economics. So the first one is Andrei Atanov, who is number what in the joint rating in Faculty of Computer Science? Number 1, 2, 3?
I see, yes.
Yes.
It's better to close this window.
He was number 1.
The last one.
The last one.
The last one from which end? Okay, so each speaker has 15 minutes, yes, and about 5 minutes for questions.
You can just close this window using red button.
So we don't ask questions during the talk.
No, we can, because this is not official defense, official defense.
So, my name is Andrei. And I will tell you about my course work, so ensemble approximation, and especially Bayesian ensemble approximation. So,
Did you switch on
red
the clicker?
button. Doesn't work.
Still?
Did you turn it off?
Yes.
Turn it
Everybody
on.
knows.
On
There
the side
should
there is
be-
a switcher.
So yeah.
Not this one. Yeah, good.
So we consider supervised learning, discriminative model. We define parametric model which produce the distribution over y. So and we define prior distribution over parameters of our model. So then we observe data, the pairs of x and y. So and infer posterior distribution. So and to be true Bayesian, we and at test phase given test point x and y. So we marginalize out our parameters using posterior distribution. So to get a posterior predictive distribution. So it is a good way to introduce weight uncertainty and weighted different model and make ensemble. So, but when DNA comes, so this guy became intractable, and so hence this guy too. So and it's time to approximation. The simplest one is to use Monte Carlo approximation. So we sample model from posterior distribution and average their predictions. So to this approximation be precise enough, so S the number of the model should be big, very big. So one way to produce a lot of samples from posterior distribution for free. So it's using stochastic gradient Langevin dynamics. So
It's not for free. More or less efficiently, but not for free.
like stochastic gradient descent. So this method connect two techniques: stochastic gradient ascent, this guy, and Langevin dynamics, which introduce normal noise in such way that the subsequence of theta t converge to posterior distribution. On the image you can see, I'm sure you see, is bimodal distribution, two-dimensional, and black dots is samples produced by this method.
And here's the gradient is strict, not stochastic one.
Stochastic.
Here already stochastic.
Yes.
So then please note that this is one of very few scalable MCMC techniques. Unlike, say, Metropolis Hastings or Hamiltonian Monte Carlo, these techniques can be formulated in terms of stochastic gradients and thus can be scaled.
Yes, you just need to add noise at each step. But the ratio between variance and learning step here is 2, but actually it maybe like hyperparameter to approximate for good approximation. You sometimes you need to use not 2. So,
And what will change? In all cases, there will be samples from the same distribution or not.
So, in my experiments, so with one-dimensional problem, so the true posterior was like this one, and with ratio of 2, I estimated posterior like this one with bigger variance. When I change constant to 4, so I have more precise approximation.
But what are the theoretical guarantees? There should be some proof results.
Yes.
At which case we will generate from the true distribution.
Look, this iteration can work in infinity, so with in infinity. So
Okay, yeah.
there is no.
So at
results
infinity,
that-
we'll end up with a true distribution.
Yes, yes.
But the problem is that
Yes.
until we reach infinity, we may generate from the wrong distribution.
Yes, we might.
Mm-hmm.
So it's more accurate posterior predicted density estimation than just using map, so maximum posterior. So it produces good estimation of weight uncertainty. It's very easy to implement. You just need to add normal noise at each step of stochastic gradient descent. So, but at test time, it's S times slower, and memory requirement bigger because of you need to store all parameters, and you should inference all models to get output of this model. And as I mentioned, S should be big enough, like 1,000 or hundreds of thousands. So the idea is to approximate ensemble by one model, which produces the same output as all ensemble. So one technique to do this is so-called distillation. So there you can see an overview of this technique. So we have teacher model, which is cumbersome one, and it can be ensemble of models, like in our case. And we have student model, which is faster and smaller. So we inference teacher and student, so and use teacher output as ground truth for student. Compute loss, so we can use whatever loss we want to optimize parameter of student. So, but in our case, teacher and student produce distribution over labels, and we use scale divergency. It's natural. So, and in case of classifications, loss will be cross entropy. So then we compute gradient with respect to student parameters and backpropagate. So one let's consider the task of image recognition, so classification. So the so we when we use this technique, we should use soft target. So because soft target contains more information, and it helpful to students. It is more helpful for students to train to distill knowledge from teacher model. So let's look at the image. So teacher very confident about its answer. So and
But is it an answer of a teacher or just a label?
so it's just so the probability of one label chip is almost one. So they very confident in its
But this is
answer.
still probability.
Yes,
This is
yes,
not
yes.
argmax.
Yes,
And you deliberately put T, temperature,
yes, yes.
in
So-
softmax in order to make it less contrast, because then it will be easier for the student to emulate
So,
teacher.
yes, yes. When teacher says that, okay, it's the main object is ship, but it's also maybe track or automobile, so it's easier to student to distill knowledge from teacher model. So,
Is the track transporting a ship?
yes. Or dog that look like cat, maybe.
Maybe some specific kind of cat.
So let's continue. So and what we want to train student neural network, which approximate posterior predictive distribution, which is an ensemble of teacher neural networks. The natural way for choosing clause is Cayley divergence between two distribution produced by student and posterior predictive distribution. We can't. So this formula analytically intractable. So, but it have form of expectation over all possible models. So, of loss on each of them. So, and we can use Monte Carlo approximation. So, where big theta is a set of models we produce, which samples from posterior distribution. So, and it's just loss on each model and actually on one X, so one object. So we need to integrate it out. So we need to average on all possible objects. So and there is appear another one expectation over objects, and we use Monte Carlo approximation, and here we have loss.
So actually we're using mini batching.
Yes, mini batch. So
This is why it's called double stochastic procedure.
yes,
So we have two types of stochastic estimates.
in
Go on.
we can know data distribution. If we know data distribution, we can compute.
Yes, but generally we do not. We know the
Generally no.
large training sample.
I have a question regarding the previous slide. Why did you choose this scale divergence and not the reverse one? Can you motivate this particular choice?
No,
Except that it's probably easier for you to optimize.
I think about it. I thought about it. So actually, it's not my choice. It's not my choice. And I think about the choice.
It's
So-
choice.
And
So it's
Maybe
prior-
it is
prior
better to
work, right?
synthesize it.
This is prior work, right? This is work of Max Welling and his students.
No, didn't remember.
It is.
Yes.
Okay, well, maybe they motivate this choice somewhere in the paper.
Ah. So this is Monte Carlo approximation of average gas divergence between two distribution. So and it's precise when the number of models and the number of objects is big enough. So and as I mentioned, we but it have form of sum of losses defined on one model, one object. So and we can use stochastic gradient descent to optimize this loss. So to produce a lot of models, we use stochastic gradient longitudinal dynamics. So all we can use dropouts because if we look at this loss, so it's just ensemble. So dropout actually produce ensemble of models with shared ways, and actually we can use different technique to produce ensemble and distal knowledge from this ensemble. So and X shouldn't be labeled, and we use unlabeled data in big amount. So and here we are. The algorithm is very simple. So we sample mini batch from train data set to make step stochastic gradient longitudinal dynamics. So we do step in noisy direction. So and we get produce next sample from posterior distribution. So then we sample data for student from any student data generator. So it could be the same data as we use for training teacher. So in my experiment, it worked well. Better than.
Sorry, one question. If you first make a step of update theta and then use the same object to like the you get the output from theta t, right?
Yes, yes.
Okay.
To train the student, I use output of teacher model.
Teacher model with
Which-
parameters theta t, right?
Yes.
Okay. Because if you use the theta t plus 1, then it would be biased.
Oh, actually, I should see that. Why?
So the bias would come because you would so you update the parameters of your teacher model using some object, and then you make another pass and look at the outputs on this particular object. So of course it would work better on this object than on a different one.
Mm-hmm.
But if you use parameters theta output with parameters theta t, then it's all right.
And if we use another object, would it go
Also-
right?
Yes.
It will also be biased because we've already seen it in the previous epoch.
It depends on the object. Maybe we have not.
Well, usually we did like why it would be conceptually different.
Well, in theory it will be biased, but probably in practice I don't think we'll suffer from this
Of
bias.
course, it will like the training loss is going to zero always, and the test loss doesn't.
The training was for MIP network, not for the ensemble.
Okay.
And here, teacher is ensemble, not MIP.
Okay.
So then we just make a step of stochastic gradient descent to optimize student parameters. For student mini batch and current teacher model. So for dropout, we do the same thing, but use not normal noise, but Bernoulli noise on activations. So here are some results. So this result on stochastic gradient longitudinal dynamics. So I use Muniz problem and linear architecture. So the blue curve is the student neural network. The orange one is teacher models. So and actually teacher models is the score is for teacher models which is sampled from posterior distribution. It's not, it doesn't convert to map estimation. So it should be.
So this is a single member ensemble, right?
Yes.
The yellow curve.
So the score should be high, but still under blue line.
Mm-hmm.
So
The blue line is ideal situation. So this is no, not the blue one. The green
green
one.
line is
So this is a result of our ensembling,
yes,
and the blue line is the result of our simulation ensemble.
yes, our student network.
Mm-hmm.
So we can see.
Looks quite impressive.
What is LeNet? You sure it's written this way? Because the only LeNet I know is called is after Jan LeCun, and he has only one E in his name.
That's
That's nice.
That sounds Japanese.
Chinese.
So another one results on CIFAR problem, and I use dropout to produce teacher models, and architecture is VG, like so it's VG for CIFAR problem. So we can see the same.
And what's the baseline for MAP network?
Yeah. I have the same question.
What is the result of MAP? What would happen if we trained MAP network? MAP maximum posteriori.
So,
So single network instead of ensemble.
actually, here teacher neural network converts to MAP because of dropouts. We
What?
use dropout, not stochastic gradient longitudinal dynamics, and each model. So here teacher neural network convert to here MAP.
But why didn't you use stochastic longevity here?
I use, but results don't ready.
Uh-huh.
Sorry, what is the final accuracy of ensemble here? Yeah, I also have the same problem.
It's about 90.
It's not about 90, it's about 87.
It's worse than.
Just one problem with the same architecture. We had
Yes.
have 93.5 with binary dropout ensembling. So it looks like that
I
you
can
should pay a
produce-
little bit more attention on your.
I think we can try applying the results of entry to your results.
Yes, but now it seems that net.
Are you sure you use
Isn't
the same
converged.
architecture? It
Y-
is
yes, I sure.
BGG-like.
Yes,
thing.
yes, I'm sure because Andrei asked me about give him source code for this architecture, so it probably
So
it is the same.
actually I can't convert teacher network to be 1991.
Okay, I think you'll be able to coordinate your efforts
Mhm.
with Arsenio and his team.
But does it really matter the particular accuracy here? We
Yes.
just compare ensemble with SNN.
We have a risk that we have an undertrained single network.
Yes, it really matters just because one architecture can achieve this result level of result. So, but if you if you trained it in a wrong way, so finally you can get absolutely wrong result with absolutely wrong interpretation.
Yes, but
It may happen that
It may happen.
we may improve our untrained result with ensembling,
Yeah,
but we will not be able to improve our result if we train single network in a perfect manner.
yeah.
Yeah.
There's a risk that this may
oh,
happen,
yes,
and you should check it.
yes, but I can't.
Now you can, because we have results by Arsenian and his colleagues.
Yes, but
Understand that it is hard, but
it still doesn't.
Okay,
No, but I try.
proceed,
Try.
please. You're running out of time.
So yes, thanks for that.
Very nice.
this is great.
Okay, any more questions?
So again, as I said previously, do not make this kind of slides. Never thank audience for attention in slide. Just say thank you for attention, but in the end you should stop at the slide at least summary of your results, that you've done this, this and that, and you achieved these results.
Artyom is right. Last slide with the words thanks for attention is considered to be monotone. So do not do that.
There is problem with size of font on your plots. It's really hard to catch it, even from the first line.
Okay.
And the last slide with results would be really important
Mhm.
because I don't understand whether do you have here some own results or you just take a known method and implement it and make experiments.
So the results is the own results is so yes, I apply results on NIST, and we apply this technique to drop out, to produce ensemble, and to make experiment.
The question was a bit
But
different,
now,
so probably I will answer. This was known method, knowledge distillation from Max Welling, and there was some previous non-Bayesian work on the same topic. So our task, the task of Andrew, was to check whether the results are reproducible and to understand that ensembling can really improve the results. If it is so, to check that ensembling has can really improve the results, and to check whether we may simulate ensemble of networks with a single network. On both cases, the answer seems to be positive. And this is very cool, because it opens, well, new ways for further research.
Anyway, it's better if you use some known method to put on the slide, on the title of the slide, the reference, so we know that this is some known method, and this is something new if you introduce some new ideas.
True. Okay, who's next?
me.
So let us thank the first speaker.
Okay, hello to everyone. My name is Artyom Veletsky, and I want to introduce my coursework, which called Conditional Generations of Words Definition, which was done under supervision of Ilya Yakubovsky and Dmitry Vetrov. This is the outline of my talk, and now let's proceed to the formulation and motivation of our work. Recent research in natural language processing showed that recurrent neural networks are state-of-the-art models for text generation tasks. They allow us to generate syntactically correct but not always meaningful sentences. Also, one important task is mapping words to some distributed vector spaces for further use in machine learning models. Mikolov and the others showed that such operations between such vectors work like operations between meanings of words, and it looks like good. It looks pretty good, and our hypothesis was that such spaces contain more semantic information about words, which we can use for conditional text generation. Now let's talk about what are recurrent neural networks and word embedding spaces in details. In many practical applications, input or output are sequences. For instance, text data is also modeled as a sequence of tokens, word or symbols, which is encoded as a one-hot vector. The vanilla recurrent neural network processes the sequence of input vectors using this formula, where f is the nonlinearity, such as ReLU or hyperbolic tangent, for example, and wx, wh, and vh are weights shared between time steps. And this fact allows us to process sequential data of an arbitrary length. The output of recurrent neural network depends on task we are solving. And for our purposes, we used softmax function because we need a probabilistic distribution over words in model vocabulary. In many papers, it was shown that vanilla recurrent neural network has some problems with gradients during training procedure, and because of this, we used a bit more complicated model called LSTM, which allows us to solve the vanishing gradient problem, and we used also gradient norm clipping to solve the gradient explosion problem. LSTM cell has the following architecture based on the gating mechanisms, and these formulas for computing hidden states. In our work, we used hyperbolic tangent as this function and the softmax. Okay, now let's talk about word embeddings. The original skipgram model was introduced by Mikolov, and it is based on the distributional hypothesis. If words occur in similar contexts, then they have similar meanings. This model is a set of grouped word prediction tasks, where each task is predict one word v given another word w and parameters theta. Theta are the set of input and output representations of words in our dictionary. These individual predictions are grouped in a way to predict context y given the corresponding word x. And the skipgram objective function is the likelihood of all contexts given the corresponding words. This likelihood is optimized using stochastic gradient ascent procedure, and then after training, input representations of each word are treated as word embeddings. Now let's look on this formula, and as we see, it is hard to compute in case of big dictionaries because it is linearly dependent on the size of the dictionary. Because of this fact, it is substituted by the hierarchical softmax. It is this formula. Now output representations are no longer associated with words, but rather with nodes in the binary tree, where each leaf is a word in our dictionary, and with unique path from root to the corresponding leaf. This function ch of n is a node, is a function that assigns 1 or minus 1 whether the node is a right or a left child of the previous node. As we can see, this approach is bigger than this simple, because now computation of this formula is logarithmic in dictionary size, because we use binary tree and its depth is logarithm of asymptotically logarithm of size of our dictionary. But this model maintains only one vector per word, but there are words that have much more than one meaning. For this task, we will use an extension of this model called adagram. And firstly, it is assumed that each word has k-meanings, and a Latin variable z is introduced. Z is the index of meaning of the word. As we see, this assumption is not really realistic, because it is not realistic to assume that each word in dictionary has equal number of meanings. And because of that, and also we want the number of meanings for each word to be determined automatically during training procedure. For this purpose, authors of the models propose a definition of Dirichlet process using via stick breaking approach for defining the prior probability over meanings of a word. And this model assumes infinite number of meanings for each word. But as we have the finite amount of data, only several meanings will have non-zero probability, non-zero prior probability. The joint probability of this model can be written as follows. Then it is optimized by stochastic variational inference, optimizing variational lower bound. And Q of Z and beta is the fully factorized variational approximation to the true posterior distribution. Okay, after training, we need some operation called disambiguation. It is getting the most probable meaning of a word using its context. We will need this in the future. Okay, now we talked about the models that we will use in our work. The one more important task in text generation is generations or sampling. And the most simple way to generate next word is to get the argmaximum of the modeled probability distribution. But this approach has some problems with that we will have only one sample, and it's really hard to find the mode of the model distribution. And because of that, we will use another approach called beam search. Instead of getting only one argmaximum sample on each step, we get k most probable. And then on each step, we condition of k previous sequences and take k most probable tokens. Then we choose top k sequences from getted as k squared using the joint probability of I plus 1 tokens, and repeat this procedure to get the sample of required length. Okay, now we can sample, and let's talk about the data that we use and the model. As the main data for our work, we used 40,000 definitions from WordNet, which is a lexical database for English words. And we used English Wikipedia for pre-training our model, because the main dataset is too small for obtaining good language model. Our model vocabulary is topmost frequent words from English Wikipedia, and the other words are chained to special unknown symbol. Also, I should say about our input vector, our input vector structure. First 300 cells is a corresponding vector from neural network embedding layer, and on the pre-training step, second 300 cells are zeros. Okay, this is the when we pre-trained our network, we start to use our first model. In the first model, we will use second 300 cells in this second 300 cells, we will use the vector from pre-trained skip-gram models corresponding to first token of each sequence. Okay, and we will train this model by
Why corresponding to the first token?
because our sequence looks like this. It is x1 is the word, and then it is the definition of word.
Ah,
So we want to
Okay.
so we want to condition.
and by the way, another question. How long is typical definition? Is it just one sentence, several words, or there are definitions?
Each example here, it is a definition,
Yes.
and definition has approximately 20 tokens.
20 tokens.
And it's quite.
I'm not sure that we need LSTM for this.
I don't know why the RNN, vanilla RNN doesn't work, but LSTM work better.
Because we need more
Uh,
hidden units in
Maybe, but this pre-training was 1 week long with 3-layer LSTM. Maybe we can train RNN, but this is only pre-training, and we want to learn language model, and then use it for modeling the generator of definitions. Okay, and also such hack as with probability p change ith token in the sequence on unknown symbol helped us to train the network. And on the test step, we condition our model in the same way and start to generate definition of words. And there is a result for this model. And these are results for test words. These words model didn't see and training step.
Are these results carefully selected?
Yes. Because we have some problems with sampling procedures. We want to improve this. But
But it would be also interesting to see at failure cases, to see where the model fails and try to understand why.
I don't put it on the slides.
And also, it would be interesting to see like the closest words that were used in the training to this one. So maybe you had like slopey in the training, and now you explain slope.
For the failures, it was noticed that the words in the definitions are the words that are close enough to the word in word-to-vec space. So failures are not so bad, but it's not the definitions of words. Yes.
So the recurrent neural network generated definitions of closely related words to the given one, but not to the given one.
Yes.
Yeah, and even if some variant of the given one was presented in the train set, the model is token level, right? So it doesn't know that slopey and slope has the same root. For the model, it's two different tokens.
Right.
Yes. As I said earlier, this model can't generate definition of words with more than one meaning. For example, words bank a spring has more than one meaning, and this model can't do this for these words, only one meaning. And we use other gram vectors in the same way for model 2. But firstly, we get the meaning vector m using disambiguation operation. We disambiguate first token using its definition, and then get the meaning vector and use it as the condition for our training procedure.
This is exactly what we have discussed, Michael.
Yes, yes, and it is work too. We use the same hack, and after training we get this result. Now we can generate different meanings. I should say that this meaning was on the training step, but it was reformulated. But these meanings are not in the train set, and this model can generate different meanings, and for Spring too. It was I didn't put it on the slide, but one more funny definition of word law. It is position of government. It's funny. Yes, and as we see, these models work, but we have some problems with sampling procedure, and we want to improve this. Also, some numerical.
And there are some problems with grammar.
What?
With grammar, there are some problems with grammar.
With grammar?
Forms
Yes,
of
yes, 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 yes. These models have such problems. And some numerical results. We measured following metrics on the validation set. First one is a mean logarithm of probability of generating the correct definition on the training set. And below is the metric from machine translation, which measure matching between sequences, between true sequence and predicted sequence, with matching n-grams between these sequences, and also penalizes different lengths of sequences and etc.
So the higher the better.
Huh? Yes,
The higher the
the higher the better. They both. And as we see, Adagram model is a bit better, but these metrics are not so interpretable that if for example this is much better than this one, we can say if the generation would be better. So let's go to the summary and the future work. We propose two models for conditional generation of word definition, and one of them allows to generate definitions for different word meanings, if they exist. And we showed that word embeddings help for conditional text generation. In near future, we want to do more numerical experiments showing the advantage of Adagram model, because visually it works better, and improve quality of samples and Adagram disambiguation. Code will be available soon at this link. Thank you for your attention.
Any questions? Yes.
Are there any baselines?
Oh, no. No, we didn't see papers, so...
Can you think of any other attempts to solve this problem? Because on the previous slide you had two lines with metrics, but they are not interpretive. You can't look at the mean and log probability and say, wow, that's a good result.
Yes, that's the main problem.
So maybe you need some superior method that is very hard to train or very expensive, that is obviously working well, or reverse, some very simple and hacky solution that works
Yes,
not so well and correspondingly has poor performance on these metrics.
Yes, I understood that.
To put it in a contrast.
Yeah, as a baseline, it would be a good idea to use.
But first we need to invent.
Yes, we want.
Actually, our main motivation here was even not to establish some new model for solving new tasks. The main motivation was different. We would like to invent some tool for examining word embedding algorithms, word embedding models. Because we know that there are many models that build word embeddings. But the question is, what is contained in this word embedding? We know one simple way of revealing some dependencies which can be contained in word embedding. These are algebraic operations in terms of embeddings, such as king minus man plus woman equals queen. This is good, this is interesting, but well, this is quite poor tool actually. Especially when we start talking about generalizations of word embeddings, when we try to build meaning embedding. And then it's quite interesting. For example, if model finds 3 meanings for the word bank, what do they correspond to? Okay, we may guess that one meaning is probably bank with a river. And the other meanings are probably somehow related to bank as financial institution. But what's the difference between them? And this is quite interesting tool, which allows to generate definition according to the vector presentation. And it simplifies us the problem of understanding what's going on. So this was one of our motivations, and this is why I do particularly like this work, because now we can understand better what's going on, and to understand better what meanings computer considers to be significant.
Absolutely, yes.
Just one suggestion. So it's better to include also kind of bad example.
Yes, I understood.
Just
Yes.
because it is just
For
good
comparison, okay.
yeah.
Yes.
Because sometimes bad examples
Very funny.
actually are quite good. For example, this famous paper by Hinton, the Krzyzewski and Sutskever, where they had bad examples. For example, dog sitting behind the cherries. And the right answer is dog, and the neural network classifies image as cherries. This was quite impressive error, actually.
Yeah.
But there is no cherry class in ImageNet. I don't know how they got this.
Maybe it's not cherry, really, but there was some.
Small hack.
Yes.
Like, do you keep track of exhaustive ability of your model? Like, for example, can you go to the previous slide? So you list 2 definitions for Spring, for example, and there is at least one more definition for it. Do you somehow like take it into account, or?
The number of definitions of words is defined by the adagram, adagram procedure. If we go to the adagram back, as we see here, it is assumed, it doesn't work, it is assumed infinite number of definitions per word, but when we have a finite amount of data, only several meanings will have non-zero probability. So we only can train adagram model in a way to get the number of meanings for each word that we want. We can't control it through the language model.
So in short, the number of meanings is discovered by computer automatically.
Yes.
And of course, it can make mistakes and estimate the wrong amount of meanings.
By the way, how do you tune alpha here?
I didn't tune. I asked Sergei Bartunov to give me models.
A good number.
Yes.
Yes.
That was
1.3.
that was, and we have some problems with that because there are many words with many meanings, many different meanings, and one of the problem is that now these meanings are quite mixed between others, between each other. So we should fix it for training our model and tuning this alpha.
So one suggestion: you should probably compare your models with unconditional generation models, where you just have a language model, and then you can compute like just language model an LSTM trained on some corpus, and then you can compute log probability of your definitions, right? So and that should give you a very reasonable baseline.
This will be quite big baseline, according to the text which is generated
Yes, but
now.
if you claim that your conditional model actually learned something from this conditioning, you should just compare with model without such conditioning,
agree.
right?
Yes. Okay, thank you.
So this will be useful, for example, if we decide to publish results.
But I don't think you can compute blue score this way.
What? Blur?
Yeah, so it will
Why?
only give log probability.
No, I think we'll find something. The most strange here is that, well, at least for me, is very slight advantage of adagram versus log2vec. I would expect much better advantage.
Is there a lot of words with different meanings?
No, on training step, all words are unique.
On test.
On test we choose word and.
I mean,
no.
you can
in this
metrics
in
only
these
for
measures.
words with different
No. In
meanings.
these measures, the words are too unique. They are unique too, with unique meanings. there are no words in test set with different meanings.
So there are no ambiguous words in test set.
And then why the grammar should work better?
We assume that
This is not exactly right, as far as I understood.
why?
I
On
don't
Uh,
understand.
when we
For example, assume that the word bank is absent in training set. Just assume.
okay,
But we still have definition, this one definition for the word bank, right?
yes,
It was present in training set, but we have excluded subset of objects for the validation, right? Because these numbers are for validation set.
yes,
Yes. So we have excluded some objects for which we knew the definition from the training set. And assume that the word bank was one of such words. Then we run adagram. Adagram has found, say, 3 meanings for the word bank. So the question is now how to compute minimal probability for the vector representation of the word bank.
yes.
We have 3 different vector, right? So we perform, by the way, what are you performing here disambiguation or simply
This
taking
is
arguments?
no, it's disambiguation.
So this is absolutely correct procedure.
Yes.
Good.
Katya, what is the question? Why the first question was about if there are words in test set with different meanings, yes?
Am I right? The test set is like a number of words with definitions for these words. Yes?
No.
It's text.
No, it's a definition from this data set.
Okay, and is there some words with different meanings in the test set?
Yes, but in the test set only one meaning is represented.
And how you choose which one you take from adagram?
We perform disambiguation.
Disambiguation. This separation.
Okay, you have 3 meanings. Which one you have? Which one you take?
Okay, let's
I'm sorry. maybe it's
example law
situation.
position of government. We take law and
We take law 1, law 2, law 3.
Mhm.
yes, and
So we
compute this
have 3
probability.
definitions.
No, we have 3 embeddings.
3 embeddings. Okay.
In validation set, we have just one definition.
One definition. We take word
Because there are no harmonics in
and
validation set.
and compute this probability. This probability show us the probability of a meaning given of a meaning of a word given the context. So we disambiguate.
And then we compute the word probability of generating this
This-
particular
yes.
definition.
Condition on meaning vector.
I'm not sure that this is right.
Why?
Any alternative suggestions? We
We,
need somehow to disambiguate.
we took argmax between all possible meanings, but it is not.
And this was bias procedure.
Yes.
So it gave more advantage, but it was not correct. So disambiguation seems to be correct.
Maybe you could see that, maybe you could look for most probably joint configuration, whatever that means.
Joint of between
Joint of meaning and the low probability of the definition.
What?
You mean probability of prior probability of the meaning?
Yeah, it's not clear how it would factorize.
We could marginalize probably between different definitions, but this again would give us
Weighting average.
yes, with prior probabilities of a particular meaning. But again, this would give us biased estimate, and this time pessimistically biased.
I mean, I don't really understand why in this case adagram should work better.
Because we
It should be
we think that adagram space is contain more information about words and relations between them than the word to express.
I will explain you later.
It's hard question, yes.
No, actually, not hard. If we're using single word embedding for the word, say bank, it either reflects mixed representation between different meanings, like Bank of the River, bank as a financial institute, or it reflects just one meaning and ignores all alternative meanings.
Yes, in this
Oh,
way,
okay.
adagram model is better.
Could you like test Adagram and Word2Vec, like your models with Adagram and Word2Vec, or not on the whole test set, but on the test set on the words which has different meanings in
No,
Adagram?
no, I didn't.
I mean, in this case, Adagram will be much better for these words.
Yes, this nice test.
But it's
Yes.
not fair.
Wait.
Why not? Because
It is
like,
fair.
I mean,
If
maybe
we-
there is no
if we include,
a big difference because there are no many words with different meanings in this set.
Yes, it
Wait,
is fair because if we
There is single definition for word, but the word itself can have multiple meanings,
Yes.
and only one meaning has definition.
But maybe in your test set, like 99% of words have has only one meaning. Then why your score should be better with Adagram? It shouldn't.
It should be the same, yes.
Yeah.
But there are some words that have several meanings.
And I think that you
And for
you
the-
can
for
make
the-
the
for these
same
words,
testing
yes,
only
yes.
for these words.
yes, it would be
Would be a
fair
good result.
because yes.
Okay, let us do that. Maybe we'll gain much more advantage. Okay, let us thank Artem. Now the last speaker, Polina.
1 minute.
Так, ты скинул, да?
Нет.
Вот это вправо, вот это влево, это подсвечивает, но она хреново работает. Да. Кирич. Ну да, ну да. Она же подсвечивает красивенько. Да? Да. Да? Да. Спасибо. Окей.
Good evening, everyone. So I'm going to talk about the project we've been working on for the past few months with Ekaterina Lobachova. Its subject is the vanishing and exploding gradients in recurrent neural nets, and in particular the effect of the constraint, the positive definiteness constraints on the recurrent weight matrices.
Вот туда и.
Computer is over here.
Just like Rage Quest.
It's better switch on.
Yeah.
I'm not sure, but
Was it you? Oh no. So, Artem already has presented what the RNNs are, but I will repeat shortly. So, they are the neural network architectures that are designed for working with sequential data. They have connections in the hidden states that are binded through time. And so the internal hidden state is computed as nonlinearity applied to the recurrent matrix, which is applied to the previous state, the internal state in the previous timestamp, and the current input plus some bias. So these networks are usually trained using backpropagation through time, and it's actually the good old backprop, just with the errors propagated back along the whole sequence, which is given to the network. And the problem arises here when we compute the gradient of the hidden state at time t with respect to the hidden state at time k, where k is like much earlier than t. So we get the product of the recurrent matrix, and it's also multiplied by the diagonal matrix, which contains the derivative of the nonlinearity. And we can see that the recurrent matrix is in the power of the distance between these two timestamps. So it goes exponentially. And it can be proven that it is sufficient for the largest eigenvalue of this matrix to be less than 1 for the gradients to vanish. And if the gradients explode, then it's necessary that this largest, with respect to the norm, the largest eigenvalue to be more than 1. And so there exists a lot of different ways to alleviate this problem. Some of them tackle both vanishing and exploding gradients. For example, we can parameterize the recommend matrix with a unitary matrix, so the norm just stays equal to 1 throughout the learning. The exploding gradients usually are tackled using gradient clipping, and for the vanishing gradients there exists a lot of solutions such as special gated architectures, LSTM and GRU, regularization terms, and different initialization tricks, which I will be talking about more precisely. For example, we can initialize the recommend matrix with identity matrix or with normalized positive definite matrix. And there were a few papers regarding this initialization and studying the effects of this initialization recently.
I have a question regarding the previous slide. Can you please go back?
Yes.
So you said that only weights of the only eigenvalues or singular values of this matrix W affect the exploding or vanishing of gradients. But what about F? Because you also have products of diagonal matrices corresponding to the derivative of the activation function.
No, I haven't decided about the non-linearity so far. I just said that if...
Yeah, but can they, even if you have awesome transition matrix that has that is always unitary and always, has all the nice properties you want it to have.
For example, identity one.
Yeah, can F still mess things up?
Yes, this claim is only as I have written. This claim is relevant when we assume that F is just identity mapping.
Okay.
So we can prove mathematically that if F is identity mapping, then for gradients to vanish, it is sufficient for the largest eigenvalue to be less than 1, and it's necessary to be more than 1 for an explosion. Okay?
Okay.
Okay. So yeah, actually it's also very important to choose a proper nonlinearity for the recurrent layer, and in these two papers that talk about identity and normalized positive definite initialization, they mark that it is a good choice to use the Verloux nonlinearity as a non-saturating nonlinearity, whereas, for example, for the sigmoid or tangent function, the gradients are very close to 0 in the major part of the number line. So if we use the Verloux, we will have this term equal to 1, and we are good, and we only need to control this component. Okay. So now I'll be talking precisely about the paper improving performance of recurrent neural nets with Verloux nonlinearity. So what they did, they said, okay, let's initialize recurrent matrix with normalized positive definite matrix. Precisely, let's make it positive definite with the largest eigenvalue equals 1 and the other eigenvalues less than 1. What was their motivation? Yeah, it did work. If we have the negative eigenvalues, we are using Verloux nonlinearity, and if we have negative or complex eigenvalues with the assumption of no input, we will shortly collapse to we will shortly collapse to 0. And if we have the normalized positive definite matrix, we will collapse to a manifold of the lower dimension, namely for the dimension
Which
where
corresponds to the largest
does
eigenvalue.
eigenvalue equals to 1. Yes.
But I haven't got the matter. Negative eigenvalue, what do you mean? You mean at least one negative eigenvalue or all negative eigenvalues?
At least one.
At least one. And what about its absolute value? If its absolute value is more than one, and I have doubts that...
But normalized, like...
So all eigenvalues are between, have absolute value of less than one,
yes,
or equal.
Yes, because
And
this...
we have negative eigenvalue, so maybe you mean here negative eigenvalue which is largest with its absolute value, no? And then we need to
Could you say again, please?
assume the following situation. Our largest eigenvalue equals to plus 1.
Okay.
And we have some negative eigenvalues. For example, one negative eigenvalue equals minus 0.1. Will we have this situation or not?
Yes. We will probably have. Like if we have vectors that are turned, like if we apply the matrix with negative eigenvalue, we get turned. Because of ReLU, we collapse to 0.
It's all because of ReLU.
So this is all about ReLU nonlinearity. As we assumed, this is a good choice for our situation.
Can you please repeat the overall claim? Like, if you have negative eigenvalues, then you collapse to 0, right?
Yes, you will most probably collapse to 0.
If you have complex eigenvalues, what will happen?
So without ReLU, the vectors are just turned around, and with ReLU, they are also collapsing to 0 for this reason.
Okay.
So this was quite a promising motivation for the authors of this paper to initialize the recurrent matrix with normalized positive definite matrix, which was done in this way. So we sample the matrix on the standard normal distribution, then we make it positive definite, and then we scale this matrix plus the identity by the largest eigenvalue of this matrix, so that we have all the eigenvalues except 1, less than 1, and only 1 equal to 1.
But you've said that if you have eigenvalue which is like positive but less than 1, you will you're guaranteed to collapse to 0, right?
In this direction, but we have we will collapse to the direction corresponding to the eigenvalue 1.
Oh.
Okay. So the authors tested this initialization on a number of toy problems. So we start from the initial problem. We have a sequence of two-dimensional sequence as the input. So the first sequence is just the number sampled from standard uniform distribution, and the second sequence is the mask, where we have only two non-zero numbers. And so our target is the sum of the numbers when we apply the second sequence, the mask, to the random signal. And so we will compare a few different initializations on this task. So I will refer to SRNN as a random Gaussian initialization, IRNN as identity matrix initialization, and RNN normalized initialization, where we can have the negative eigenvalues, but all of them are less than 1 for the absolute value, and normalized positive definite initialization, which is the proposal of the authors. So they have this histogram in the paper where they have plotted the number of correctly predicted sequences, where they name the correctly predicted sequence is the sequence when you have the the error less than 0.004 something. And so you can see that the NP RNNs perform at par or better than like any other initialization. But when we try to reproduce the results using the same architecture as was described in the paper, we were unfortunately not able to get the same quality. And well, you can see that RNNs are the yellow lines on every graph. They perform much better than any other initialization. And yes, so for the sequences longer than 100, all the initializations except RNNs just are stuck in the constant solution, which is 0.17 around so.
A few questions. First of all, if you initialize the matrix with identity, do you have to somehow break the symmetries to make everything learnable?
No. No.
Because all other weights are like all other except the current weights
are not
random, so-
symmetric. So they break symmetry. Data
other
terms
weights.
break symmetry.
Oh, okay. And the other question is, are there intuition in the paper why their initialization is better than identity? Because identity is also like non-vanishing and very good, right?
They have results.
I mean, was there any intuition? Like why? I mean, you can throw
Well,
any.
no.
I don't know. Okay. Just like let's try this. It will not be bad because of this theory, but like
Yeah.
let's hope it will be good.
Yeah,
Okay.
like that. But, well, so we have got the results that NP RNNs are sort of worse than RNNs. And, well, we could have stopped at this point, but we did not for a number of reasons. First of all, it was April already. The second reason is that, well, we can see that when we compare NP RNNs and N RNNs, we can see that NP RNNs always perform better. However, the distribution of the norms of eigenvalues for NP RNNs and N RNNs is the same. So we can still have some fake hope that maybe positive definiteness would make any good for other tasks.
I'm sorry, I missed it. What is distribution of what is the same?
So the distribution of the eigenvalue of the norms of the eigenvalues.
Oh, so like eigenvalues are different, but the norms are the same.
Yeah.
Absolute values.
Absolute values, yeah.
Yes.
I mean, because we think that NPRN doesn't work as good as IRN because of the distribution of eigenvalues. So.
Okay, so you notice that the distribution is of absolute values is the same, and
So maybe there is some
other factor.
like positively definite.
So positively definite performs better than just normalized matrix, just normalized initialization.
So
wait, no, but you mean NP RNN
NP RNN,
performs better than just N RNN.
yes,
But you have already I RNN, which performs much better
yes,
than both.
yes.
But we will start
But
to like.
the first reason, it was already April.
No, we will. Now we will speak not about initialization. So.
Yes.
Okay. Please proceed.
As NP RNN performs better than N RNN, we can hope that there may be some good factors of positive definiteness.
Oh, okay.
So we can probably try and make a constraint on the positive definiteness of the Riemann matrix and see what we get.
Uh-huh.
So yes, well, let's make a positive definite parameterization of the WHH matrix as follows, and let's just take gradients with respect to x, and we can also start from different initializations here. We can start from the identity matrix because it's also well positive definite, and we can start from just an arbitrary positive definite matrix. And I'm sorry for
do
this.
you want to also constrain normalized part of the NP?
No.
Why not? Like I mean, this weight normalization thing kind of hints us that.
How would you make the constraints on?
I mean, weight normalization worked, right? So when you decouple the vector and the norm of the vector into separate variables, so you can do it and
It's
just.
like different idea.
No, I mean, you started from that you want to make your matrix positive definite and normalized. So why not to try to force it?
I would say so. This is our future work.
Okay.
I'm sorry, is X just a full matrix, or because I think you can just use lower triangular matrix, right? Like in LU decomposition.
Yeah. Sorry, say again.
Is X a full arbitrary matrix?
Yes, just
or-
a full matrix.
Because you can just use a lower triangular matrix.
Lower
right?
rank. It would make it
Singular?
singular.
Well, not necessarily.
Why?
Well, because it will be in, singular if and only if there is zero value on the diagonal. Because the determinant of a lower triangular matrix is exactly a product of diagonal terms. What Michael was saying is that there are known decompositions of matrices into products of triangular matrices. And this is a nice property to have because you have twice a lower number of parameters.
Okay.
Actually, you assume to know that any symmetric positive definite matrix can always be represented as a product of two triangular matrices.
Yes, I know that.
And why not using that? If you want to.
From the simplest one.
Okay, so the advantage of that would be that you can guarantee that it's positive definite and not positive semi-definite. So if you say that on the diagonal the values are non-negative, they're positive, then you're guaranteed that that you will have no zero eigenvalues.
But why do you care?
I'm just looking at positive definite matrix, and the result may not be positive definite. So okay, just ignore this. I'm not sure.
Okay, please go on.
Yes. So, but when we take the gradient with respect to x, we would have another scale because now we have the quadratic dependence on x. So, like for these experiments, we use the same hyperparameters as stated in the paper, and now we would need to perform the grid search to understand how we optimize this task. But it turned out that, sorry for this slide because I don't have enough comments here, it's a last minute slide. So by the row I vary the gradient clipping, and by the column I vary the learning rates, the same for the second picture. So
So it's
What are the
useful
curves?
to have axis labels.
what?
Axis labels. Because I'm not sure what is x-axis and what is y-axis. So this
So it's the same as here. It's just the epoch and the MSE on test. And so the best performance is.
What are the curves? Because it's
The colors.
So the colors is the blue for Ironen for simple initialization, and the yellow for constrained positive definite matrix.
From Ironman's
From initialized from the identity matrix. And the best performance is here for Ironen. It wasn't anywhere else for this picture and the next slide for a normalized positive definite matrices. And well, we can see that positive definite constraint doesn't make any visible benefit for the learning, and moreover it's very unstable, and so it can be properly seen here as these are the error for every iteration of the learning, its gradient norm, and the maximum, median, and minimum eigenvalues of the recurrent matrix. And for constrained matrices, the gradients are exploding very significant. And well, we can see that for iron ends, when we have exploding gradients, after a few steps we start, the loss starts to decrease, and we converge to some good point. However, it doesn't happen in the case of the constraint matrix. We just have the exploding gradients, and we are stuck in the region with this high scalable gradients, and we cannot escape from it. And for the constraints on the from the initialization of normalized positive definite matrices, we have another problem of the vanishing gradients. So the gradients are very low, and the distribution of eigenvalues hardly change over the learning. And well, so the best performance here is from IronN. Another task we tested on was pixel by pixel mist, and surprisingly here IronNs and constrained IronNs perform at par, and but normalized positive definite IronNs converge to a very, very bad minima, and which is also not consistent with the results which we saw in the paper about NP-RNNs, which is quite sad. And also on pixel by pixel permuted mist, when we perform a random permutation on pixels of every picture, it is considered to be a more long-range dependency task. And here the performance is quite comparable to the previous slide, and we have the IronNs and constraint IronNs performing comparable to each other, and NP-RNNs performing much worse than them. And when we applied this to a text generation task on Shakespeare dataset, we got some other results where NP-RNN performed better than any other initialization or any other metrics, but the matrices that were constrained to be positive definite performed much worse than those that were arbitrary. So
The activation was too low.
Yes, everywhere the activation was really low. And yeah, so they also had very unstable gradients there, so we hypothesized that that's the problem of this constraint. And the conclusion is that unfortunately we were not able to reproduce the results of the base paper, but however it was showing good results on the practical text generation task, and the constraint was not a good idea so far, and it led to unstable gradients and bad performance.
So do you understand right that
Oh, you have said.
that the rule of thumb would be to use identity matrix as the initialization?
Yes, but it's also very unstable because it for problems like this, like the text generation, I have seen a few papers that were saying that IronNs were performing very unstable due to the exploding gradient problem. But
Because of identity initialization?
because we are sort of more prone to go for eigenvalues that are more than one.
Right. This is true. But anyway, your experiments show that identity initialization works more or less,
Yeah.
at least in comparison with other initializations you explored. And another conclusion is probably that constraint of positive semi-definiteness makes the procedure less robust.
Yes.
Again, this is quite intuitive one.
For initialization. Actually, it's a good question because, as you see, on the top problems with very long dependencies, IRN works better. But on more real-world problems like Shakespeare dataset, like language model for Shakespeare dataset, and PRNN actually works better.
Well, they're more or less comparable.
Maybe, but I saw some results with more like more difficult architectures, and there and PRNN was much better.
So, but then
So
we can't
maybe-
claim that the
maybe-
results are completely irreproducible.
It's not. I think it's because the fact that in real world problems, the real world problems actually are not only about long dependencies.
Mhm.
And this third problem is about long dependencies only.
I see.
And the
But
results.
it means that well, we do not care about vanishing gradients in real world problems if the dependencies are not so long.
Ali mentioned the
But you can
results
reference
were,
the results from the papers.
yes, for the
I've got that.
long range problems.
But that's not your fault.
Hope so.
I would suggest that you try some Bayesian optimization of hyperparameters for the addition problem, because it might be that, I mean, then you can make an objective claim that, you know, the one method is better than another because you do not have the bias that you yourself tune the hyperparameters. So, in general, I think it's either you use just the same hyperparameters for all methods when you know that they are good for all the methods, or you try to use some automatic tuning technique.
But I mean, in the paper they used the same parameters,
Um,
and we also used the same parameters.
Okay, so
It doesn't work.
For producing the paper results, we used the parameters that they used, but then
just typing in the hyperparameters from the paper does not always work, because sometimes different, for example, the optimizer might be implemented slightly differently. The default parameters that they did not claim in the paper might be different. So it's not a very good idea to just try the parameters from the paper and hope that they work. It might not be the case, unfortunately.
Your implementation is different.
Some people say that Bayesian optimization only works if you have more than 1,000 samples,
Yeah,
more than 1,000 iterations. So unless you have computational budget to do so, there is novel work that's called Hyperband, and its authors say that it's very good hyperparameter optimization algorithm.
How long does it take to run this experiment on addition?
which one?
This one,
Addition, just around an hour.
around an hour. So maybe you can just run it like 10 times faster.
Well, depends on the length of the sequence.
Yeah, maybe you can just choose some short sequence, and then maybe you can run hyperparameter optimization. Because yes, Artem is right. You need to run at least several hundreds of training iterations for Bayesian optimization to work.
I have a question concerning optimization. What about using hyperpriors?
What?
Hyperprior.
Priors?
Hyperprior.
Hyperparameter.
Are you suggesting some kind of hierarchical model?
But hyperparameter on what?
On regularization, maybe.
Are you suggesting hyperprior just for the sake of hyperprior?
Just to be more basic.
More hierarchical. We need to go deeper.
It's always better.
Well, it seems that if you change an activation function, all the results should be repeated. Yes.
Yes, of course, because all these tricks for like initialization, they
Graduation.
for a rule. Because if you use tangents, then your norm of this diagonal matrix, this non-linearity is less than zero, less than 1.
Well, tangent is
Like
different,
1/2
but
like this.
if you take a leaky ReLU or
Oh, maybe.
exponential ReLU,
Maybe.
all these are similar to ReLU, but it seems that they change the results here with utilization.
But we can't even reproduce the results with the ReLU. the results which were obtained under the strict assumption that this is real.
This
But
way
wait,
you can just ask authors to send you code.
I have
We don't
mailed
have-
authors and they wished me luck.
They said that they wrote this code in some company and now they
They no longer work for this company.
Good luck.
It was Qualcomm
Куда нет,
research.
но вы там держитесь просто.
Yeah.
Okay, any more questions? If not, then let us thank the speaker. So I'm quite content with the speakers. Sorry.